Large neural models perform well on benchmarks, yet as we increase scale, they collide with an invisible barrier. They cannot formally verify their own reasoning. Contemporary foundation models, like large language models, are designed around statistical sequence prediction. They ingest massive text datasets and calculate the probability of the next word. But calculating probability is a form of blind imitation. The model maps patterns in the data, but it builds no internal representation of the causal physics governing the real world. Adding more parameters to an opaque neural network increases its capacity to memorize, but it offers no architectural mechanism for compositional correctness, the structural guarantee that combining valid logical steps will always produce a valid final conclusion. To build a system capable of general intelligence, we have to move away from black box weights. We need an architecture where logic is explicit, auditable, and subject to mathematical proof. This is the design objective behind Al-Sabīl. It is an architecture engineered to support verifiable reasoning through its internal structure. Instead of a massive matrix of continuous numbers, Al-Sabīl operates as a hypergraph foundational model. A hypergraph is a mathematical structure where a single connection can link any number of distinct concepts simultaneously. This diagram illustrates the system's structure. Rather than acting as a single, uniform monolith, Al-Sabīl processes information through a 7-tier cognitive stack. The lower levels handle basic perception and predictive world modeling, while the higher tiers govern complex operations like long-horizon planning and autonomous self-modification. The 7-tier stack organizes intelligence into a series of explicit checkpoints. This transforms capability growth into a governed software engineering process, where each new skill must be validated by the layers below it. The foundation of this system begins at Tier 1, the universal computational substrate. This visualization shows how the model represents its internal state. It uses a discrete hypergraph, allowing it to capture multi-way relationships between objects at the same time. Real-world data is noisy and incomplete. To reason accurately without breaking the system's logic, we have to split the architecture into 2 domains, the ontic and the epistemic. The bottom plane is the ontic layer. This contains the system's deterministic structural beliefs about reality. It represents the strict physical states that the model accepts as fact. The top plane is the epistemic layer. This acts as an overlay to track where information came from, measuring source reliability and assigning confidence scores to every piece of incoming evidence. Keeping these domains separate allows the model to process conflicting reports or uncertain observations without overwriting its established knowledge base. Confidently, the AI calculates probabilities and weighs uncertainties in the upper layer while preserving the deterministic nature of its core reasoning kernel. Moving to Tier 2, we look at how this rigid structure adapts over time. At any given moment, the predictive world model uses its existing graph to forecast what the environment will do next. When an observation contradicts the model's prediction, the system generates a predictive residual. A residual is the exact mathematical difference between what the AI expected and what actually occurred. In this architecture, that residual acts as the explicit, quantifiable trigger for the learning process. Instead of adjusting continuous weights across a vast network, the induction engine isolates the specific error and generates formal structural proposals to explain the mismatch. These proposals might suggest creating a new relational edge between 2 existing data nodes, or they might define a new macro program to handle the novel logic. Learning in Al-Sabīl consists of discrete, auditable structural revisions that remain legible to human engineers. Once the system generates these structural hypotheses, it needs a way to mathematically arbitrate between them to decide which rule is correct. Every learning event is governed by a strict constraint called the minimum description length, or MDL. MDL is a mathematical principle stating that the most accurate model of a dataset is the one that compresses that data most efficiently. The system tests each proposed rule on the balancing scale. It will only accept a structural change if the new logic compresses the observed data better than the existing baseline, proving it adds real utility. Because the state is represented explicitly, the model can execute bounded, non-myopic compositional reasoning. This means it evaluates the long-term logical consequences of a rule, not just the immediate next step. It simulates futures and runs state transitions through the proposed graph structure before ever committing the change to memory. If a revision passes the test and is merged into the system, Al-Sabīl logs a derivation trace, creating a permanent causal history of exactly why its knowledge changed. Relying on the MDL protocol ensures that capability growth is a conservative, evidence-driven process that protects the system against data hallucination. The principles of explicit structure and verification become vital at Tier 6, which handles the challenge of autonomous self-improvement. To modify its own code safely, Al-Sabīl relies on a unique mechanism. The system represents its own software architecture and cognitive logic as an explicit hypergraph itself. Structural self-modification follows the same workflow as modeling external data. The AI proposes revisions to its own governing graph, which are then subjected to rigorous evaluation. These self-directed proposals are intercepted by a module called the meta-arbiter, which uses protected evaluators to quarantine the new code. Inside this sandbox, the proposed modifications must survive the same MDL verification criteria. If the new logic causes regressions, it is rejected. It only deploys if the metrics turn green. By treating its own architecture as an explicit, auditable dataset, the system ensures that recursive intelligence remains mathematically bounded, preventing uncontrolled architectural degradation. At Tier 7, the architecture expands from a single agent into a population-scale network. In this environment, independent Al-Sabīl systems accelerate discovery by exchanging successful structural rules. They do this by transmitting signed transfer artifacts, cryptographically verifiable packages of proven logic. Al-Sabīl replaces standard parameter averaging with a protocol of signed transfer. Agents exchange successful structural rules as independent artifacts rather than synchronizing their internal states. The process enforces a rule of local re-verification. When an agent receives an incoming artifact, it must independently test that logic against its own local MDL criteria. Only after passing the local check is the new knowledge integrated. This creates a non-coercive federation. Agents specialize in different tasks and share findings, but a corrupted agent cannot force its flawed logic onto the rest of the network. Collective intelligence requires trust. By insisting that knowledge exchange relies on verified epistemic provenance rather than consensus, the architecture scales safely. The current industry reliance on opaque AI is a specific engineering choice, not a mathematical inevitability of scaling up compute. The hypergraph framework of Al-Sabīl demonstrates a structural solution to the verification gap. It establishes an unbroken progression, starting at a deterministic substrate, moving through conservative, trace-logged learning, and culminating in a governed framework for federated collective reasoning. At every level of scale, the model maintains its causal truth. Engineers retain full rollback capability and structural auditability. As we approach systems with general capabilities, the architecture proves that intelligence does not have to be an inscrutable oracle. It can remain structurally interpretable, verifiable, and strictly anchored to reality.